How often do the greatest scientific breakthroughs arise not from a direct search, but from an unexpected glitch, a ghost in the machine? Consider the vast digital ocean of astronomical data constantly being trawled by automated sentinels designed for a very specific purpose: planetary defense. On the summit of Haleakala, the dormant volcano on Maui, Hawaii, stands one such guardian, the Pan-STARRS 1 telescope. This technological marvel was never built to seek out visitors from beyond our solar system. Its primary mission, deeply rooted in Cold War-era strategies, was to spot potentially hazardous near-Earth asteroids, cataloging them long before they could pose a threat. Yet, this sophisticated system, a testament to 21st-century engineering, ceaselessly scans the entire visible night sky every few nights, generating petabytes of raw data. To put that into perspective, a single petabyte is equivalent to 1,000 terabytes, or roughly 250,000 DVD movies. This colossal volume of information far exceeds human capacity for direct analysis, a vision of automated celestial mapping first conceived by astronomers like Fritz Zwicky in the 1930s, but only truly realized in our modern era. The Pan-STARRS 1 system is a tireless digital eye, sifting through cosmic noise, searching for anything that moves. It was into this digital realm, on October 19, 2017, that Canadian astronomer Robert Warwick logged in, not anticipating a momentous discovery. He was merely performing a routine check of anomalies flagged by the system's Moving Object Processing System, or MOPS. This intricate software is programmed to distinguish between the countless ephemeral blips that populate its data stream, the fleeting trails of cosmic rays, the momentary glints from Earth-orbiting satellites, and the subtle, consistent movement of genuine celestial bodies. It does this by meticulously comparing a series of images taken minutes apart, searching for the telltale progression of an object truly traversing the void. What the algorithm flagged that day was not a cosmic ray, nor a satellite, nor even a typical asteroid. It was a faint, moving point of light, one that defied all conventional classifications. The discovery of this object, which would later be named Oumuamua, was, therefore, a magnificent accident, a specter caught by a digital net designed to catch fish, yet it somehow snared a bird. The initial detection was baffling because of the object's trajectory, a hyperbolic path, a mathematical signature that screamed of an unbound traveler. This curve, first mathematically described by Pierre-Simon Laplace in the late 18th century in his seminal work on cometary orbits, indicated that this object was not gravitationally tethered to our Sun. It was merely passing through, briefly bent by our star's immense gravity, before continuing its journey back into the interstellar abyss. Consider the sheer improbability of this find. It is akin to searching every single beach on Earth, sifting through trillions upon trillions of grains of sand, and by chance unearthing one unique grain that originated from a distant, unknown planet. This single, unexpected blip underscored a profound truth that guides all scientific exploration. Our greatest discoveries are profoundly shaped by the very tools we build and the specific questions we think we are asking. Often, these tools, and the data they provide, lead us to answers for questions we never even conceived. In the frantic initial hours following the alert, Robert Warwick and his colleague, Marco Micheli, worked against time. They delved deep into the archival Pan-STARRS data, tracing the object's path backward, frame by painstaking frame. With each confirmed position, the evidence solidified. Its interstellar origin was proven beyond any doubt. This extraordinary visitor was then given its official designation, 1 IU 2017 U1. The I stands for interstellar, signifying its unprecedented status as the very first interstellar object ever confirmed by humanity, a landmark moment etched forever into the annals of astronomical history. This was not the start of a sensational story about unidentified flying objects. This was the beginning of a profound scientific detective case, where the first crucial clue was nothing more than an unexpected anomaly in an immense, digitized ocean of cosmic observations. The instant the data confirmed an interstellar visitor, the clock began ticking. Observatories across the globe, from the European Southern Observatory's Very Large Telescope in Chile, its colossal mirrors poised on the barren Atacama Plateau, to the Gemini Observatory perched atop the volcanic slopes of Mauna Kea in Hawaii, turned their immense eyes skyward. They raced against time, desperate to capture every fleeting photon from this cosmic enigma before it vanished back into the profound depths of the interstellar void. What they gathered in that frantic week was not just a stream of data. It was a bizarre, contradictory narrative unfolding in the language of light. The first and most striking puzzle emerged from the object's extreme light curve, a scientific term describing its rapidly changing brightness. Unlike any asteroid or comet known within our solar system, Oumuamua's luminosity surged and dimmed with astonishing ferocity, fluctuating by a staggering factor of 10 every 7.3 hours. This radical shift in brightness, meticulously championed and analyzed by astronomers like Karen Meach of the University of Hawaii, offered a profound clue about its fundamental form. This data suggested a shape dramatically unlike anything seen before, highly elongated, perhaps 10 times longer than it was wide. A cosmic cigar, some mused, or perhaps, even more unusual, a flat pancake tumbling end over end through the abyss. Such a chaotic rotational state, physicists inferred, hinted at a turbulent past, a history of violent collisions or powerful gravitational encounters that had sent it spinning uncontrollably across light years. But then came an even more baffling revelation, one that elevated the mystery to an entirely new level. Data meticulously collected from the venerable Hubble Space Telescope, orbiting high above Earth's obscuring atmosphere, confirmed a subtle yet undeniable truth. Oumuamua was accelerating away from the Sun. This was not the simple gravitational tug-of-war expected from a passive object. It was propelled by a force that could not be explained by gravity alone. This phenomenon, known as non-gravitational acceleration, became the true crux of the entire mystery, defying all conventional understanding of celestial mechanics. In our solar system, such non-gravitational acceleration is typically the signature of a comet. As a comet approaches the Sun, its frozen volatile materials, like water ice or carbon monoxide, sublimate under the increasing heat, turning directly from solid to gas. These escaping gases create powerful, rocket-like jets, propelling the comet forward and forming the characteristic dusty, gaseous halo known as a coma, and often a spectacular tail. This process is well understood, the physics precisely defined, and the spectral signatures of these gases clearly detectable. Yet, despite extensive spectroscopic analysis, led by dedicated teams using powerful instruments like the William Herschel telescope on La Palma, no trace of such activity was found. There was no visible coma, no dusty halo, no outgassing jets. Scientists meticulously searched for the expected spectral signatures of water, carbon monoxide, or even common dust, but Oumuamua's spectrum remained stubbornly featureless and uniformly reddish, a profound and direct contradiction in the evidence. It was as if the cosmic object was performing an impossible trick. In a cosmic crime scene investigation, the clues were simply not adding up. We had a getaway vehicle, the object itself, unmistakably speeding up as it departed our solar system. But its engine, the cometary jets that should have been roaring and visibly active, was utterly silent and completely invisible. This left the scientific community in a state of profound bewilderment. Oumuamua was breaking the established rules, defying the very definitions that separated asteroids from comets. It was forcing a fundamental, unsettling reevaluation of what kinds of objects could drift through the vast, cold interstellar void, and what unknown forces might be at play. The cosmic detective story deepened as scientists, faced with the baffling enigma of Oumuamua, began to consider every known natural explanation, one by one. Each theory, initially promising, found itself under intense scrutiny, much like a suspect offering an alibi that soon crumbles under the harsh light of interrogation. The fundamental challenge remained: how to explain an object that was not merely tumbling, but also mysteriously accelerating, without any visible sign of propulsive activity. One of the first and most appealing natural suspects was the unusually dry comet hypothesis. Perhaps, some proposed, Oumuamua was once a typical comet, but its surface ices had long since been depleted, or it was composed of exotic materials that outgassed invisibly to our telescopes. This seemed like a neat solution, offering a familiar category for an unfamiliar object. Yet, the physics of celestial bodies presented a formidable counter-argument. For an object of Oumuamua's inferred size, estimated to be perhaps a few hundred meters long, it would be almost impossible for the sun's radiant heat not to penetrate its outer layers and trigger some form of visible sublimation if any significant amount of ice remained. Think of a large block of ice left in direct sunlight. Even if covered in dust, the heat would eventually melt or sublimate the ice, producing a visible vapor or leaving telltale residue. For Oumuamua to behave as an ice-driven comet without any observable signs, it would require an extremely rare and improbable composition or structure. Next, the scientific community interrogated the highly unusual asteroid theory. Could Oumuamua be a fragment, a cosmic shard from a planetary body shattered by a stellar collision in a distant solar system? This idea offered a plausible explanation for its extreme elongation, a shape unlike most asteroids we observe. A colossal cosmic impact could indeed generate such an odd, elongated piece of debris. However, this theory instantly faltered when confronted with the most critical piece of evidence: the persistent, non-gravitational acceleration. Asteroids, by their very nature, are inert rocky or metallic bodies. They have no known internal mechanism to generate the kind of sustained thrust observed in Oumuamua. The idea of a mere asteroid accelerating away from the Sun defies the fundamental laws of celestial mechanics as we understand them, leaving this suspect without a credible alibi for the propulsion. As the more conventional explanations failed, astronomers were forced to consider increasingly exotic, yet still natural, possibilities. One such idea suggested that Oumuamua was an object of extraordinarily high porosity, something akin to a cosmic dust bunny or a fragile cobweb of interstellar material. If it were light enough, perhaps even lighter than air, then the subtle pressure exerted by solar radiation alone could, theoretically, account for its acceleration. This solar radiation pressure is a real, albeit weak, force that pushes on all objects in sunlight, but its effect is usually negligible on dense bodies. Could Oumuamua be so incredibly tenuous that this minute force was enough to push it? Calculations from brilliant researchers like Roman Rafikov at the University of Cambridge, published in a 2018 paper, explored this very concept. His work demonstrated that for solar radiation pressure to provide the observed acceleration, Oumuamua's density would have to be implausibly low, far less dense than cotton candy. Such an object, by extension, would be so incredibly fragile that it would be unlikely to survive the rigors of its long interstellar journey, let alone the gravitational stresses and impacts it might encounter. It would simply disintegrate. Then came another elegant, albeit daring, proposal in 2020, the primordial hydrogen iceberg, put forth by astronomers Darrell Seligman and Gregory Laughlin. This theory suggested that Oumuamua could be a chunk of frozen molecular hydrogen formed in the ultra-cold conditions of a dense molecular cloud between stars. The beauty of this idea lay in its ability to explain the non-gravitational acceleration without a visible coma. As solid hydrogen sublimes, it would produce an invisible gas, providing the necessary rocket-like thrust without any detectable signature in optical telescopes. However, this promising solution faced its own formidable challenge. Subsequent studies revealed that such a primordial hydrogen iceberg would have evaporated far too quickly in the diffuse interstellar medium over its assumed journey of millions or billions of years. Think of an ice sculpture left out in a vast, dry desert for eons. Even if the air is cold, the sculpture would eventually vanish, leaving no trace. A hydrogen iceberg would simply not survive the immense timescales required to traverse the galaxy. Each of these explanations, from the dry comet to the hydrogen iceberg, represented a serious, rigorous scientific attempt to solve the profound puzzle of Oumuamua. Each hypothesis was conceived by brilliant minds, meticulously studied, and subjected to the harsh scrutiny of data and physics. Yet, each one ultimately required us to assume that Oumuamua possessed such a rare, specific, and unlikely combination of properties that its very existence would be, in its own way, a statistical miracle. It was as if every natural suspect in this cosmic lineup had an alibi that, upon closer inspection, turned out to be riddled with inconsistencies, leaving the scientific community cornered in a room with a seemingly impossible problem. The universe, a vast, silent canvas, often presents us with puzzles that defy the very frameworks we build to understand them. When the search for natural explanations for Oumuamua, the first confirmed interstellar visitor, led only to dead ends, a profound intellectual vacuum began to form. Every conventional theory, from the dry comet to the invisible hydrogen iceberg, failed to fully account for its bewildering characteristics, especially that undeniable, uncomet-like acceleration. Into this scientific void stepped a figure who would challenge the very foundations of astronomical thought, proposing a hypothesis so audacious, so controversial, that it would echo through the hallowed halls of academia and reverberate across the globe. He was not a fringe figure, nor a sensationalist seeking headlines. This was Avi Loeb, at the time the esteemed chair of Harvard University's astronomy department, a prolific and highly respected theoretical physicist. Loeb's impressive career had spanned the cosmos, delving into the most profound mysteries of the universe, from the enigmatic nature of black holes to the grand architecture of the early cosmos. His scientific credibility was, by any measure, unimpeachable. Yet, in 2018, he co-authored a paper with his colleague Shmuel Bialy, posing a question that many in the scientific community considered taboo. Could solar radiation pressure explain Oumuamua's peculiar acceleration? Their proposal was elegant in its simplicity, yet revolutionary in its implications. What if Oumuamua's observed acceleration, that mysterious push away from our sun, was not due to outgassing, but to something far more deliberate? What if it was a solar sail? Consider how a gentle breeze pushes a boat across a lake. Now, scale that concept to the cosmos. Starlight, though seemingly massless, actually exerts a tiny, measurable pressure on anything it touches. This phenomenon, known as solar radiation pressure, was first theorized by the visionary Johannes Kepler in the 17th century, who noted that comet tails always point away from the sun, as if pushed by an unseen force. Its existence was later experimentally proven by the Russian physicist Pyotr Lebedev in 1900. A solar sail is, in essence, an incredibly thin, ultralight membrane, perhaps just a few micrometers thick, designed to harness this faint but persistent pressure of starlight for propulsion. Think of a sheet of aluminium foil stretched to an extreme thinness, then expanded to cover an area equivalent to several football fields. Such a structure, if lightweight enough, could be gently, continuously pushed by the photons streaming from a star, accelerating without the need for rocket fuel or visible exhaust. Loeb and Bialy argued that if Oumuamua were such an object, its extreme thinness and large surface area to mass ratio could perfectly explain its observed non-gravitational acceleration without any need for outgassing or a visible coma. The core of Loeb's argument was a logical deduction, a journey guided not by preconceived beliefs, but by the relentless pursuit of what the data demanded. Since every known natural explanation, every usual suspect, had failed the interrogation, leaving an unfillable gap in our understanding, should we not, as scientists, be compelled to consider the possibility that Oumuamua was artificial? His conclusion was a stark challenge to the prevailing scientific orthodoxy. If the simplest, most elegant natural explanations cannot account for the evidence, then perhaps the explanation lies beyond what we currently define as natural. This position, however intellectually sound it might seem to some, placed Loeb in a venerable yet often uncomfortable lineage of scientists who dared to propose paradigm-shifting ideas. Recall the arduous struggle of Alfred Wegener in the early 20th century. He proposed the theory of continental drift, suggesting that Earth's continents were not static, but had slowly migrated across the planet's surface over geological eons. For decades, his revolutionary idea was met with scorn, ridicule, and outright dismissal by the geological establishment, who scoffed at the notion of drifting continents. It was only many years later, with the accumulation of overwhelming evidence from seafloor spreading and plate tectonics, that his theory was finally accepted, fundamentally reshaping our understanding of Earth. Loeb's hypothesis, therefore, brought into sharp relief the intricate sociology of the scientific community. There is an undeniable giggle factor that often accompanies any serious discussion of extraterrestrial intelligence, particularly within mainstream astronomy. The field of SETI, the search for extraterrestrial intelligence, has historically been viewed with skepticism, often marginalized, starved of funding, and considered by some to be on the fringes of legitimate scientific inquiry. This institutional bias creates a powerful inertia, a reluctance to consider possibilities that might be perceived as unscientific or too close to science fiction. And so, the central question crystallizes, framed by what has come to be known as the Galileo Gambit. Is Avi Loeb a modern Galileo? Courageously speaking a truth the establishment is not yet ready to hear, despite the potential professional and social costs? Or is he making an extraordinary claim, one that requires, but lacks, the requisite extraordinary evidence? Critics from within the scientific community swiftly countered Loeb's hypothesis, arguing that invoking aliens, however elegantly reasoned, is ultimately an argument from ignorance. When faced with an unknown, they contend, the most scientific answer is simply, "We do not know," rather than immediately leaping to, "It must be technology." This pivotal chapter in the Oumuamua saga transcends a simple aliens versus nature dichotomy. It elevates the debate to a more nuanced philosophical inquiry into the very nature of evidence, the inherent limits of our imagination, and the profound courage required for any scientist to propose a truly unconventional hypothesis, especially when it challenges deeply ingrained intellectual comfort zones. The question remains, how far are we willing to let the data lead us, even when it points to something truly extraordinary? The cosmos, in its infinite complexity, often demands that we stretch the very limits of our understanding. When the bold, some might say audacious, hypothesis of an artificial origin for Oumuamua was put forth by Harvard's Avi Loeb, it did not just provoke debate, it served as an unexpected, powerful catalyst. This intellectual gauntlet, thrown down by an eminent astrophysicist, ignited a remarkable wave of creativity within the planetary science community. It compelled researchers to transcend the boundaries of the usual suspects and envision entirely new, more exotic, and previously unconsidered natural explanations for this enigmatic interstellar visitor. Among this flourishing of second-wave theories, one particular hypothesis emerged as profoundly compelling for its elegance and ability to address Oumuamua's baffling anomalies, the nitrogen iceberg theory. Proposed by astronomers Alan Jackson and Stephen Desch in 2021, this idea suggested a cosmic origin story as fascinating as it was unexpected. What if Oumuamua was not a mere comet or asteroid, but a colossal shard of solid nitrogen ice, much like the surface material that covers the distant dwarf planet Pluto or Neptune's largest moon, Triton? Such a fragment, they posited, could have been violently knocked off an exo-Pluto, an icy world orbiting a star in a young, turbulent star system eons ago, sending it hurtling into the interstellar void. The core ingenuity of this nitrogen iceberg concept lies in its ability to elegantly resolve Oumuamua's two most perplexing puzzles. First, the non-gravitational acceleration. As Oumuamua passed through our solar system, the sun's faint warmth would have caused the solid nitrogen on its surface to slowly sublimate, or turn directly from ice into an invisible gas. This process would generate a subtle but consistent thrust, much like a tiny, unpowered rocket engine. Crucially, nitrogen gas is transparent to our telescopes. It does not form the dusty, visible coma or tail that characterizes traditional comets, perfectly explaining why Oumuamua showed no signs of outgassing activity despite its acceleration. It was a silent, unseen push. Secondly, this theory offered a satisfying explanation for the object's extraordinarily elongated shape, that tumbling cosmic cigar or flat pancake that so baffled astronomers. As a nitrogen ice fragment journeyed across vast stretches of interstellar space, bombarded by cosmic rays and tiny dust grains, its outer layers would have slowly ablated away, much like a bar of soap eroding in a shower. This continuous, uneven erosion would naturally sculpt the object over millions of years, preferentially flattening it into a long, thin shard, optimizing its shape for the very sublimation that propelled it. This was not a definitive answer, but rather a brilliant piece of astrophysical detective work, showcasing the scientific method's self-correcting and imaginative power, pushing us to consider scenarios previously beyond our conventional models. Yet, like all scientific hypotheses, the nitrogen iceberg theory faces its own formidable challenges, prompting further scrutiny and debate. Critics raise questions about the statistical unlikelihood of our solar system being crossed by such a specific type of object. While exoplutos are theoretically possible, are there enough of them, forming in young, chaotic star systems, to make the passage of such a fragment a common enough occurrence to explain Oumuamua's solitary visit? The universe is vast beyond measure, but probabilities, even in the cosmos, still hold sway. Furthermore, the very survival of such a fragile object over millions or even billions of years of interstellar travel remains a subject of intense astrophysical modeling, requiring precise conditions for its journey. Beyond the compelling nitrogen iceberg, other innovative, albeit speculative, ideas also emerged from this period of intense intellectual ferment. Perhaps Oumuamua was a dark comet, not made of typical water ice, but rather enveloped in a thick, insulating crust of organic material. This crust could have prevented any visible sublimation, even if there were some volatile substances beneath, effectively muzzling any potential coma and hiding its true nature. Another intriguing thought proposed that Oumuamua was a unique type of object formed directly in the cold, dense molecular clouds that drift between stars, a primordial wanderer created from the very raw materials of the galaxy, unlike anything we have encountered within our own solar system. The overarching theme of this scientific renaissance is clear. Avi Loeb's artificial hypothesis, controversial as it was, served as a crucial scientific catalyst. It raised the bar for natural explanations, forcing planetary scientists to move beyond the familiar and invent entirely new categories of celestial objects, expanding our understanding of what nature is truly capable of producing. This period of intellectual ferment demonstrates a profound truth about science. Even a hypothesis that may ultimately prove incorrect can be incredibly valuable. not for providing an answer, but for pushing the boundaries of inquiry, forcing us to explore new and previously unimagined territories of the cosmos. It urges us to keep looking, to keep questioning, because the universe, as Oumuamua proved, always holds more surprises than we could possibly anticipate. For centuries, the cosmos appeared as a majestic, unchanging tapestry, its stars fixed, its planets following ancient, predictable paths. This serene view of the universe was not a reflection of its true, dynamic nature, but rather a profound limitation of our own tools. Our eyes, unaided, could only glimpse the brightest lights, and our earliest instruments, however revolutionary for their time, were slow, laborious, and often blind to the subtle, fleeting phenomena that truly define the interstellar void. This begs a provocative question. Was Oumuamua, the first confirmed interstellar visitor, truly unique? Or was it merely the first one we were finally equipped to see? Long before the digital revolution ushered in rapid, automated sky surveys like Pan-STARRS 1, astronomers were celestial archaeologists, meticulously sifting through data captured on fragile photographic plates. Consider the monumental, yet ultimately flawed, Carte du Ciel project, initiated in the late 19th century. This ambitious international endeavor aimed to map the entire sky, requiring millions of glass plates to be exposed and then painstakingly analyzed. Or turn to the mid-20th century, to the Palomar Observatory Sky Survey in the 1950s, which produced another vast collection of these delicate records. The process of finding anything that moved across these plates was a testament to human perseverance and, simultaneously, to human fallibility. An astronomer would sit, often for hours on end, peering through a stereoscope, comparing two images of the same patch of sky taken at different times. Their mission: to spot any tiny dot that had shifted its position, any faint streak that betrayed movement. This manual, eye-straining task was incredibly prone to error. A subtle scratch on the glass, a random cosmic ray hit creating a brief, spurious trail, or even a minor equipment artifact could easily mimic the signature of a faint, fast-moving object. A fleeting, barely perceptible streak, much like what Oumuamua would have appeared to be, would have almost certainly been dismissed as mere noise, an anomaly in the emulsion, or simply overlooked by tired eyes searching through thousands upon thousands of identical fields. The faintness of such an object, coupled with its rapid motion, made it an almost impossible target for the observational technology of the era. But today, a new discipline is emerging from the convergence of astronomy and computer science: data archaeology. Projects like the Digital Access to a Sky Century at Harvard, known as DASH, are breathing new life into these dusty, century-old archives. Scientists are now digitizing millions of historical photographic plates, transforming them from fragile glass into petabytes of digital information. Once digitized, these vast datasets are fed into advanced machine learning algorithms, powerful artificial intelligences capable of sifting through cosmic noise with an unprecedented level of precision and tireless efficiency that no human eye could ever match. This digital resurrection opens a tantalizing possibility that ghosts of past interstellar visitors might lie dormant within these historical records. Perhaps, for decades or even centuries, these silent travelers have been captured by our telescopes, their fleeting signatures inscribed on photographic emulsion, waiting patiently for a 21st century algorithm to recognize them for what they truly are: objects from beyond our stellar neighborhood. These algorithms are programmed not to dismiss anomalies, but to scrutinize them, looking for patterns that human perception, overwhelmed by sheer volume, once simply couldn't discern. And the evidence for such hidden visitors extends beyond photographic plates. In 2019, researchers Amir Siraj and Avi Loeb published a groundbreaking paper calculating the statistical probability that some previously recorded fireballs, those spectacular meteors that ignite in Earth's atmosphere, were in fact interstellar objects of a different kind. They pointed to events like the 2014 CNEOS meteor over Papua New Guinea, an object that broke apart in the atmosphere, as a compelling candidate. This connects the profound mystery of Oumuamua to tangible evidence, meteors that have already struck our very planet, leaving no doubt of their arrival. This historical lens brings into sharp focus a profound point about the nature of scientific discovery itself, our perception of the universe, what we believe it to be, is always, fundamentally, a reflection of our technological capabilities. For the longest time, the cosmos seemed static and predictable because our tools were too slow, too crude, and too blind to perceive its true, dynamic, and chaotic nature. The arrival of Oumuamua, therefore, was not merely the discovery of a singular, extraordinary object. It was, instead, a landmark moment when our technology finally became fast enough and smart enough to perceive a phenomenon that may have been happening all along, just beyond the edge of our vision. Our upgraded cosmic senses are now picking up echoes from a galactic highway we never knew existed. When all the known paths diverge and the universe still presents an enigma, what then? We stand at a crossroads in the cosmic detective story of Oumuamua, where every natural explanation, meticulously examined, has faltered under the harsh glare of scientific scrutiny. But what if this isn't a dead end? What if the very characteristics that make Oumuamua so baffling, so stubbornly anomalous, are not contradictions of nature, but rather silent clues, whispers from an unknown intelligence? This is where the profound thought experiment truly begins, a disciplined journey that moves beyond merely asking, "What is it?" to daring to ask, "If it is artificial, what does that imply about its creators?" To embark on such a journey, we must first arm ourselves not with fantastical notions, but with fundamental principles that govern existence itself. Consider the universal driver for all evolution, both biological and technological, the relentless pursuit of maximum efficiency. From the intricate design of a bird's wing, optimizing for lift and minimal drag, to the sleek lines of a modern jetliner, every advanced system in nature and technology strives to achieve its purpose with the least possible expenditure of energy and resources. This principle, an almost economic imperative woven into the fabric of the cosmos, becomes our primary filter. Now, let us apply this filter to Oumuamua's inferred characteristics. We know it was thin, perhaps 10 times longer than it was wide, or even a flat, disc-like shape. We know it was lightweight, almost impossibly so for a natural object of its size, and crucially, it appeared unpowered, without any visible jets or a discernible coma. What does this tell us through the lens of interstellar economics? Launching any object across the vast, cold emptiness between star systems is an endeavor of unimaginable cost and complexity. It demands a propulsion system, tremendous energy, and materials that can endure millennia. If a civilization were to send a probe across such distances, their paramount concern would be efficiency, achieving the maximum scientific return with the absolute minimum of mass, energy, and time. A thin, lightweight, unpowered design, propelled by the faint but omnipresent pressure of starlight, represents the pinnacle of such efficiency. It is the ultimate low-cost, low-maintenance interstellar traveler. This brings us to a concept first formally proposed by the brilliant mathematician John von Neumann in the 1940s, the von Neumann probe. Envision a spacecraft not designed for a single mission, but engineered to be self-replicating. Upon reaching a new star system, such a probe would utilize local resources, asteroids, moons, even gas giants, to construct copies of itself, which then continue the journey, exploring the galaxy not linearly, but exponentially. One probe becomes two, two become four, and so on, theoretically allowing for the exploration of an entire galaxy over timescales that, while still immense by human standards, are far shorter than the age of the universe. Could Oumuamua be a derelict version of such a device? A piece of an ancient galactic exploration network, long since fallen silent, its mission perhaps completed eons ago, or its parent civilization now just a memory. The apparent lack of communication or energy signals from Oumuamua might seem like a strong argument against its artificial nature. After all, what kind of probe would not announce itself? But again, apply the filter of maximum efficiency and age. Its silence could be a sign not of absence, but of extreme economy. A probe designed for deep space travel might enter a dormant state, conserving power for millions or even billions of years, only reactivating if it encounters something of interest. Or, more poignantly, it could be a piece of ancient cosmic flotsam, a silent relic from a long-dead civilization. We have found echoes of human history across our own planet, artifacts whose purpose is clear, but whose creators are long gone. Consider the discovery of a Viking longship, half buried in the sand of a remote beach in the modern Atlantic. Its original purpose and origin are unmistakable, yet it is now nothing more than a silent, tumbling relic, its sails long rotted away, its crew returned to dust. Oumuamua could be a similar ghost ship, a silent testament to a journey whose purpose we can only begin to deduce. Of course, the realm of artificial probes immediately conjures up more unsettling possibilities. The Berserker hypothesis, named after the terrifying self-replicating predatory machines in Fred Saberhagen's science fiction series, posits that automated probes could be designed not for exploration, but for destruction. They would be programmed to seek out and eliminate other intelligent life. However, Oumuamua's inert passage, its apparent lack of any hostile or even actively observational behavior, makes this grim scenario highly unlikely. It simply passed through, a silent, unthreatening visitor. So, what does its tumbling, seemingly uncontrolled state suggest about its nature and purpose? Is it merely a piece of debris, perhaps a fragment from a larger, long-destroyed craft, or a defunct probe that completed its mission countless millennia ago, its power sources depleted, its intricate systems finally succumbed to the harsh vacuum of space? Or could it be something akin to a message in a bottle, a passive, incredibly durable artifact designed not to transmit, but simply to endure, carrying within it some silent information, waiting for a civilization like ours to find and decipher it. This would require an unparalleled understanding of material science and long-term cosmic survival. By applying these logical and economic filters, by reasoning from the object's observed behavior and inferred characteristics back to the motivations of a potential creator, the alien hypothesis transforms from mere speculative fiction into a rigorous deductive exercise. It allows us to construct a hypothetical profile of the civilization that might have built such an artifact. It is akin to an archaeologist meticulously examining a single pottery shard unearthed from an ancient ruin. The material, the design, the firing technique, each detail offers a clue, allowing us to deduce the nature, the technological prowess, and even the societal values of its long-vanished creators. Oumuamua, the silent, tumbling enigma, might be just such a shard, hurtling through the cosmic ocean, waiting for us to piece together the profound story it silently tells. The universe, an expanse of unimaginable scale and endless mystery, often reveals its most profound secrets not through grand pronouncements, but through a fleeting whisper. For centuries, humanity has scanned the night sky, searching for answers, believing we understood the boundaries of our cosmic neighborhood. But then, on one ordinary October night in 2017, a single enigmatic object, Oumuamua, slipped into our vision, shattered our assumptions, and left behind a legacy that continues to reshape the very fabric of scientific inquiry. Its true importance lies not in what it definitively was, a question that still sparks passionate debate, but in the fundamental questions it forced us to ask, and the audacious new scientific endeavors it inspired. This interstellar visitor, a cosmic anomaly that defied every known classification, acted as nothing less than a cosmic wake-up call. It shook the scientific community out of a long-held complacency, forcing a radical re-evaluation of the boundaries we once drew between geology, planetary science, and the most tantalizing of all quests, the search for life beyond Earth. Before Oumuamua, the idea of an alien artifact casually drifting through our solar system was relegated to science fiction, a notion dismissed by most mainstream scientists with a dismissive wave of the hand. After Oumuamua, the conversation irrevocably shifted. It became a mirror, reflecting both the vastness of our ignorance and the incredible self-correcting power of our scientific method to confront it head-on. One of the most direct and tangible offspring of the Oumuamua mystery is the birth of groundbreaking new initiatives, designed specifically to address the kind of questions this object provoked. Prominent among these is the privately funded Galileo project, co-founded by Harvard University's Avi Loeb. This ambitious endeavor is not merely a rehash of older SETI efforts. It aims to create a dedicated, systematic scientific search for extraterrestrial technological signatures, going beyond radio signals to look for physical artifacts or phenomena that might betray intelligent origins. It also includes a serious, rigorous investigation into unidentified aerial phenomena, formerly known as unidentified flying objects, applying the full weight of scientific methodology to observations that were once relegated to fringe theories. Yet perhaps the most significant long-term impact of Oumuamua lies in its influence on the next generation of astronomical instruments, particularly the Vera C. Rubin Observatory in Chile. Picture a colossal digital eye, scanning the entire visible night sky every few nights, gathering unprecedented amounts of data. The Vera C. Rubin Observatory is precisely that, a revolutionary telescope designed to survey the sky with such unparalleled speed and sensitivity that it will transform our understanding of the dynamic cosmos. Before Oumuamua, the strategies for observing and analyzing data from such telescopes were primarily focused on objects gravitationally bound to our Sun, asteroids, comets, and planets. But the sudden, unexpected appearance of the first interstellar object caused a seismic shift in planning. Scientists recognized that if one such object could be found almost by accident, then a truly dedicated, high-speed survey might reveal many more. As a direct result of the Oumuamua event, the observation strategies and data analysis pipelines for the Vera C. Rubin Observatory were fundamentally influenced, incorporating specific protocols to identify and track fast-moving, non-gravitationally bound objects. This revolutionary shift means that the observatory is now expected to discover not just a few, but dozens, if not hundreds, of interstellar objects every single year. We are no longer talking about a singular, perplexing anomaly. We are on the cusp of discovering an entirely new observable population of celestial bodies, originating from beyond our solar system. This dramatic increase in interstellar detections will give rise to a brand new field of study: interstellar archaeology. Imagine a cosmic excavation site where each passing object is a relic from a distant star system, carrying clues about its origin, its journey, and the stellar environment from which it was flung. Each new discovery will allow astronomers to build up a statistical understanding of these interstellar wanderers. Are they mostly comets or asteroids? Do their shapes and compositions vary widely, or do they share common traits? And crucially, will any of them, like Oumuamua, continue to defy natural explanation? The answers will not only deepen our understanding of planetary formation in other star systems, but also provide crucial data points in the ongoing, quiet search for something truly extraordinary. The mystery of Oumuamua, the silent whisper it sent across the vast void, may never be definitively solved. It is long gone, hurtling into the depths of space, beyond the reach of our telescopes. But its fleeting passage ignited a spark, pushing the boundaries of scientific thought and accelerating the development of the tools we need to truly listen to the universe. We are now finally building the ears to hear the next one, and perhaps the next hundreds. The cosmic detective story has only just begun, and its most thrilling chapters are yet to be written.